Hi there, my name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is the summer 2020 offering of ECE3084 Signals and Systems. We've spent an inordinate amount of time inverting Laplace transforms using partial fraction expansions, and that's historically been a big pain. But fortunately, there are some theorems that can help us if we only want to know about limiting cases of our time domain function, but don't really need to know exactly what's happening with the function for all time in general. Some particular special cases that you might be interested in might include what's happening as t goes to infinity. I'll write this colloquially as evaluating the function x at infinity with these little quotes. And the final value theorem will tell you that under some conditions, you can find this limit by multiplying your Laplace transform by s and letting s go to 0. Similarly, the initial value theorem tells us that if you want to know what x of t is as t approaches 0 from above, that's what that superscript plus means. Again, you can take the Laplace transform multiplied by s, but this time you let it go to infinity. Now, in most of the applications we've been looking at, we'll usually have the case where whatever the function is approaching 0 from the left, well, that's just what it is as 0. Nothing weird is going on there. But that's for most usual engineering applications. There may be strange functions for which that's not the case. Both of these theorems have a fairly significant caveat in that they only hold if the limit in the time domain actually exists. So it converges, and it converges to something finite. Let's take a look at an example of a dangerous case along these lines. Consider the Laplace transform big X of s equal 3 over s squared plus 9. Suppose we weren't too interested in what the time domain function this corresponds to looks like for all time. Suppose we were merely interested in what this is at infinity. My final value theorem would tell me that x at infinity, eventually I'll stop putting in those quotes, can be found by multiplying my 3 over s squared plus 9 times s and letting s go to 0, which of course would give me 0. So does the inverse Laplace transform of 3 over s squared plus 9 converge to 0? Well, no. X of t is sine 3t ut. This is the Laplace transform of an instant-on sinusoid. And what does that look like? Well, it's going to be something like this. It's going to be a sinusoid that starts at t equals 0 and goes on forever. So x of t does not converge to a sensible number. It never settles down. So as a result, you can compute this and you can get a number of 0, but that doesn't mean anything. So here is a case where that finite value theorem doesn't hold. And what's dangerous about it is you can just brute force compute something like this and get a number, but that number is just garbage. It doesn't mean anything. Now, you usually get into trouble with this when you're looking at what a function is doing as time goes to infinity. So it's a problem that we wind up running across a lot when we're using the final value theorem, but it's not something you run across a lot when you're using the initial value theorem, mostly because things are usually pretty tame around 0. Now, there are functions out there for which this doesn't hold. For instance, consider the following crazy function. What about xt equals sine 1 over t? Well, if you think about this, what is this doing? As t's approaching 0 from the right, essentially the wiggles are going to be happening faster and faster. I get more and more wiggles. Wiggle, 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 wiggle. The wiggles are getting denser. So as I'm approaching t, this never settles down. This is a weird function. I have no idea if this has a Laplace transform anyway. I would be surprised if it did. So this is probably not a great example of a challenge to the initial volume theorem, because if it doesn't have a Laplace transform, we couldn't talk about the theorem anyway. And as a practicing engineer, it will be a very weird circumstance that you would encounter this function anyway. This is just one of those examples that people in the School of Mathematics use to both amuse themselves and torment engineers. But it's kind of fun.